Okay, everybody, another one of these easy chapter 4 videos. Another this is this and that is that, and I'll try to keep this one short because I know you got to study. Alright, the law of definite proportions. We said law of constant composition was that we had a certain percentage by mass. Now the law of definite proportions comes from that. So what it's saying is, for instance, water is always H2O. It is never H2O3 in some places in the universe and H2O7 in other places. It is always H2O. And they got that from the law of composition. For instance, if we take a look at an 18-gram sample of water, we'll find that 2 grams of it is hydrogen. If we take a look at 10 times as much water, then we get 10 times as much mass of hydrogen. So again, that means that that ratio of mass must mean that you also have the same ratio of atoms in the molecule. So it's a pretty easy concept. Now, Dalton came up with this law of multiple proportions, that because if you look at the mass composition, and let's say you compare something like nitrogen monoxide, nitrogen dioxide, and then dinitrogen oxide, yeah, you're going to find that these mass ratios are constant from substance to substance, but there's only certain mass ratios you can get when you combine two different materials. With ionic compounds, there's only one combination you can get, but with covalent, there's multiple, but they're always in some sort of ratio that's based upon that mass idea. So therefore, if the masses are always in certain proportions, then that means that the particles are also in certain proportions, and that the particles must be whole numbers because we're getting whole number multiples. So in other words, what does the law of multiple proportions mean? It means that water is always H2O. It can't be H2 1.6 times, H2 1.6, and then that makes no sense. H2.6 O 1.6. It's got to be some sort of whole number ratio because we get whole number multiples of masses. Isotope. We said that Dalton was wrong. He didn't know, because he didn't have the technology, that not all atoms of the same type are exactly the same. We do have isotopes. They vary based upon the number of neutrons that they have. And the example they like to use is hydrogen. Hydrogen is the only set of isotopes that have their own special names. So we expect you to be familiar with the hydrogen isotopes. So I'm going to copy this little chart and paste it into Notability and go over it with you. All right, so let's put that there. Now let's stretch this thing. Okay. The first hydrogen isotope is something called protium. And protium is what we think of when we think of hydrogen. It makes up about 99% of all hydrogen atoms. It has one proton because all hydrogen atoms have one proton. It has no neutrons, so therefore it has a mass of 1 AMU. Its isotope notation, this is what we had in the first couple of videos. You would put the hydrogen symbol, and then you use the left side for your numbers. So your mass number goes in the upper northwest corner, and your number of protons goes in the southwest corner. But there's also an isotope of hydrogen called heavy hydrogen. It has the name deuterium, not deuteri, that just didn't fit in the chart. And deuterium makes up about 0.8% of all hydrogen atoms. Like all hydrogen atoms, it has one proton, but it also has a neutron. And it is twice as massive as a regular hydrogen atom, so it kind of has its own special chemistry. Right? Mass number of 2, 1 proton. The last is actually radioactive. It's so heavy that the nucleus falls apart, and this is something called tritium. Tritium is used as a tracer element in medicine. It creates radiation, but it's low-level radiation, so we can see where the medicine goes in your body by detecting the low-level radiation. So tritium has one proton, 2 neutrons, and a total mass of 3 AMU. It's isotope notation, symbol hydrogen, 1 proton, and a total mass of 3. Now, sometimes they refer to hydrogen in what we call nuclide notation, where we would write hydrogen and then we write the mass number, hydrogen-1. So 1 represents the mass. Deuterium can be written as hydrogen 2, and tritium can be written as hydrogen 3. So if we had uranium-238, that means that you have a uranium atom with a mass of 238 AMU. Now, if you take these masses and you average them, that's where that 1.008 AMU shows up on your periodic table. It is the average of all the hydrogen isotopes. So all your masses on the table represent an average of the isotopes that make up that substance. And then lastly, I think all we got is a review of isotope notation. All right, so isotope notation. This would be an example. Suppose we had a sodium atom, and that sodium atom had a mass of 23 and an atomic number of 11. This is something we called isotope notation. Again, another way of writing this would be to write sodium 23, and then that gives you the mass number right here. So it gives you the particle, sodium, and the mass that goes with it. So we're talking about a sodium 23 isotope. So on a test, what they would ask you is they would say, all right, well, which element it is? And obvious, it's sodium. We could look up Na on the periodic table. But then they'll ask you, hey, what is the number of protons? Well, the number of protons are equal to the atomic number, which is in the lower left. Then they ask you the number of neutrons. Well, neutrons are the total mass minus the protons, so we would have 12 neutrons. And then they'll ask you for the number of electrons. And if there's no charge, that means it's neutral, so that means it has the same exact number as the protons. So suppose I gave you this on a test. I said, hey, here's element X, and element X has a mass of 48 and atomic number 22, and it has a charge of positive 2. I want to know, first of all, what's the identity of X? What are the number of protons in this particular atom? What are the number of neutrons? And what are the number of electrons? So you can pause and give that a shot, and then when you're done, come back. Hey, you're back. Okay. So I can use the number of protons to figure out the atom. So if I'm going to write that in, 22 protons, and then I look up element 22 on the periodic table, it is titanium. And the number of neutrons is going to be the mass number minus the protons, gives me 26 neutrons. Now the number of electrons, we have a deficiency of 2. Remember, positive 2 means deficiency. That means we have 2 less electrons than we have protons, so we only have 20. And that's it. That should be a review of middle school. That's all.